Start recording. Okay. So, again, warm welcome to everybody. The speaker has joined. So, it is my pleasure to introduce Dr. Anjan Goswami, an AI and engineering leader at Microsoft USA, where he heads applied science efforts for PowerPoint Copilot. He is one of the resource person from outside India. His current work is at the cutting edge of AI, focusing fine-tuning large language models, multimodal reasoning systems, and agentic AI for enterprise applications. With over 2 decades of experience in AI and ML, Dr. Goswami has contributed to leading organizations including Microsoft, Adobe, Salesforce, Walmart, eBay, Amazon. He holds a PhD in computer science from UC Davis, where his research focused on learning to rank and bandit algorithm for search and recommender systems. We are privileged to have him with us today. Please join me in welcoming Dr. Anjan Goswami to deliver his talk. Over to you, Anjan.
Hello, everyone. Good evening. This is 5:30 a.m. in California. It's my pleasure to talk about the evolution of language model to reasoning models today for all of you. And I will try to discuss this from as much as possible from first principle and try to provide the intuition behind this very historical journey in advances in AI. And please stop me for any questions when I'll be discussing on this. Just like a few words before I start. So this is really a historical time. So we can imagine that the entire journey of AI, it started kind of in 1950s or around that time with the inception of programming languages like Lisp and similar concepts in computer science. Then the various different concepts in AI appears at that time, but what we are seeing now, this is an unprecedented advancement in AI, and it's kind of reaching a state where this is this is going to make significant changes in all parts of the society. So this is a very interesting time, and so it will be very interesting to understand like how this evolution has happened from like LLM to reasoning model today. So that said, I will start the presentation now. So give me 1 second. Yeah, let me just make sure that this slide is. Are you able to see the slide clearly?
Yes.
Yes.
Okay.
Okay.
Yes.
So, So the first I want to talk about the ChatGPT moment, which we all know around end of 2022. we see that ChatGPT was released, and we can consider that that's the time frame when everyone suddenly noticed that a very powerful AI has appeared, and what we witness that ChatGPT, right after its inception, within 2 months, it reached 100 million users. And just to give you some perspective, TikTok, another tool and another like internet phenomena, it took 9 months to reach 100 million user. For Instagram, which is a little bit like previous generation, that it took 2.5 years. WhatsApp 3.5 years. Facebook, it was like 4.5 years. So it is amazingly fast that people started using ChatGPT, and they got addicted to it, and they started using it more. So this is this has never happened, that like any application, any internet application is receiving so much adoption in so fast, so short period of time. Now, what is this ChatGPT? So, okay, what is this ChatGPT? So the chat, let me know if you can, if you are not able to view the entire slide. Are you able to view the entire slide?
Yes, no problem.
Yes. Okay. Yeah. So yeah. So what is the chat? What is ChatGPT? ChatGPT is a large language model. And what do we mean by large language model? So a large language model, you can imagine that it's essentially predicting the next word given the previous words, and now if we look at the mathematical definition of language models, then what it outputs is a probability distribution over sequences. So imagine that you have a language, and when I'm talking about a language consists of a vocabulary. Like if we think about like English language, we have the vocabulary of English languages, and then there are like rules of the languages. So a language model is something that a model, a mathematical equation. If we use that equation, that should emit the distribution of sequences of words from that languages, and in a way that it's most likely to be meaningful sentences. And then this is the equation showing in the slide. This is an important equation. So it's just showing that probability of showing a word WT given all other words before it. So you think about like it's a sentence, and then suppose you have a model for that, and the model's parameter is theta. It can be any parameter, any combination of parameters. Then how do you choose these parameters to make this text highly probable? So that's the language model, and when I'm talking about large language model, it has like a lot of parameters. Okay. Now there are 3 important concepts that we want to understand when we want to understand large language model. So we understand now that what a language model is. So it's a model of language. We want to this model can generate sentences from that language. Now the first concept is called maximum likelihood, which is very classic concept in statistics, and yes, this is a you can consider that it's a statistical model. So the first equation is the equation of maximum likelihood. Like people who are coming from statistics background, they will immediately identify this equation. These are very, very classic things. and there are many different ways of modeling this. And the log here is essentially used. It's called log likelihood, and that's basically to avoid avoid the product, right? So you had product here, and then when we're taking log, it's becoming like summation, and that's basically to avoid the like multiple products operations numerically and make it more stable. Now, the second concept is called cross entropy. This is again the information theoretic concept. So maximum likelihood is the overall. You can think about like this is the maximum likelihood is the mathematical model for languages. So in order to make a language model, we need to pick some kind of maximum likelihood model. Now, the cross entropy is another important concept, which is telling us, which is giving us a very interesting concept here, and that's basically, think about like this in this equation. What I'm saying is the Q, and then we have P inside the log. So P theta, this is basically the distribution that is generated from the model, and Q is the actual distribution, actually like how the sentence should appear. And this expression is again very classic expression. It's just giving and you know, if you think about information theoretically, this log of P theta, when you are using that expression, that's kind of the expression of entropy. And you can intuitively think about that. Suppose you have a distribution of words, so you are kind of like modeling the language. When you are modeling the language, you are generating multiple words. So imagine if language model is not correct, it will generate words in an order that will be not meaningful. So if the language model is correct, it will generate words in a way that will be understandable by everyone. Now, this when you are using this log P theta W, that expression, that kind of gives you number of bits you need to represent some kind of code. And when I'm saying code, that's kind of like the capturing the concept of language. And then this expression cross entropy is saying that suppose you need, you know, n number of bits to represent a particular distribution that is generated from the language model, and QW is the actual number of bits that you actually require to represent the true distribution, then it's just giving you, this expression is giving you how many additional bits you require to represent the distribution when you are generating through the language model. And when so this is important because in every language model, in any model, anything you pick in machine learning, you need to optimize that model. So you need to, in this case, when I'm saying maximum likelihood, you are maximizing the likelihood, and that is similar to minimizing the cross entropy. That can be easily proved. When you are minimizing the cross entropy, which is the loss function, when you are trying to optimize this equation, then you are trying to minimize the number of additional bits you need to represent the distribution. So what it means that you are trying to force the distribution towards the true distribution. That means you're trying to make the language model better. So that's the cross entropy. I'll stop here for a second. This is actually a very important concept. If there is any question on this, then I'll answer this question. Okay, so no question. So I'll talk about the next concept. This is yet another important concept which you probably hear very often. So it's called perplexity. Now, that as the name signifies, so perplexity, the mathematical expression of perplexity is actually exponential of average cross entropy of all the words, and it's kind of intuitively. Uh, so perplexity is essentially giving you a number that when it is low, that means you have less surprise for representing the language, and that just means that the language model is actually pretty good, because you don't have like you don't have randomness. You have much better order when you are generating the language using that model, and that's the evaluation metric. So in order to again, like in order to create a model, you need to any model, any mathematical model, you need to have a you need to optimize something, and that something for language model is maximum likelihood. You are optimizing for likelihood, and in order to optimize, you need to consider that, okay, how I am going to optimize, what is my loss, and the loss here is the cross entropy. And then when you have whatever algorithm or mechanism you are using to run this process, you need an evaluation metric to understand how I'm doing. And that's evaluation metric. One of the evaluation metric is perplexity. So, perplexity is a evaluation metric for languages. So, for example, you can consider perplexity of English language versus perplexity of Bengali language. If perplexity is low, that means there is less ambiguity. And perplexity of Sanskrit language, you can construct those things. Those are languages already exist. And human languages, again, if you consider programming languages, that is less ambiguous, so it will be less low perplexity. So low perplexity means the language is already in a very ordered state, and less ambiguous, and language modeling will be easier. But anyway, so these are like very related concepts and basic concepts that we need to understand. Okay, now then what we have so far now, that imagine that if you consider any language, then you want to define that language. It will be defined as, okay, I have an input sequence, W1 to Wn. That's just any word, and that's the language. That's your language. As long as that's meaningful, that's your language. All these W1, W2, Wn coming from write words from the language. So and then you imagine that you have a sliding window, and then you keep that window, and then you have some sequence of words within that sliding window, and then you want to predict what is the next word if I'm using that language. So if I'm using English language, the cat is on the mat. The cat is on the, if that is in a sliding window, then mat will be the next word. If we can predict mat, that's a good word. But then if I'm predicting dog, then that language model is not good. So and again, you can see that same sequence of word, there can be many different words that you can place which will be meaningful, but then not everything is equally probable. So I think those are the aspects you want to construct within your language model. So generally, how this is done is, you think about these words. We call it in computer science. We call it like tokens. Now, these words are, when you are modeling in computer, you need numbers, and for each word you map it to some kind of vector, and that vector typically here is called embeddings, and that goes to the model, and the model outputs vocabulary distribution. So what is happening here, that the output of the model, that is something you want to understand. The output of the model, suppose in your word, in your language, imagine your language has 10 words. Then output from the model is the given some sequence of word from that, your small tiny language of 10 words. Suppose you give your input is 2 words, and then your next word, it will try to pull one of the words from this 10 words. And how it will pull? The model will output probability of placing all of these 10 words for after those 2 words you have picked in the beginning. So you will get a probability distribution of all these 10 words, and then you pick the one with highest probability, or you can pick the second one. And in this case, imagine if it's an English language, the example I was talking about, the cat is sitting on the, then maybe like mat is one of the words, and mat has the highest probability, then you pick mat. But if instead of mat, suppose the probability, suppose there's a word called table, the cat is sitting on the table, maybe the table is the second one. So a good language model it may actually predict that the highest probability of emitting the next word is mat, and maybe the next one is table, maybe the other one is wall, and maybe the word dog coming after these sequence of words, that will have lowest probability of getting there. So that's kind of output of the language model. Okay, please feel free to ask me questions here. And I'm kind of like assuming a background, some background in this area. But I think one of the things I have not really asked, like what is the background here for the people. And, I know Dipankar told me that everyone is coming from universities, so I kind of like assumed that like you have the some background in this area, but actually maybe like before, like I can adjust the presentation a little bit if I know a little bit of the background. And I know there are so many people. Maybe Dipankar, can you help me a little bit? Like, are we? Is this all right? Like what I'm talking about, the back in terms of background?
No, many of them don't have computer science background. So, assuming that, you can proceed.
Okay. Okay. So please ask basic questions. If you think about like stop me and ask me basic questions, then I'll go more fundamentals. But I think for what we covered so far, this is actually really not particular to computer science. This is more probably statistics and very basic mathematics for this area. So okay, so let's think about like, okay, so we now know that, okay, we have a language, and then what we want to do is we want to come up with a function, and that function will help us in this task, where we feed some set of words to this function, and the function will emit some other set of words. And this entire thing magically, because the way the function is designed, it is going to generate a meaningful sentence in any language. That's a language model. Large language model is nothing that where we have this model, this equation, mathematical equation is just simply large. We have like, W1, X1, W2, X2, maybe million, maybe billion, that's a large. And we'll come to that. So that's the thing. So we have equation is emitting a vector, and this vector, each dimension is a number signifying a probability of a particular word. And think about like if the vector has n dimension, n is the total number of all the words in the language. If you want to think about intuitively. Right? And what we have described so far, that we are, how do we come up with this equation? So we kind of like need a loss in order to optimize this equation. Okay, we'll come there. So how do we choose this function? So there's a little bit of theoretical idea from this is from computer science, but it's just like maybe like you can just try to understand that these neural networks, neural networks are very special kind of function, you can I don't have a picture of neural network here, but you can think about that. You have in neural network, you have multiple layers, and you can think about it like a graph. I think that's the easiest way to think about. So if you think about it's a graph, and it's called like, you know, it will have like layer 1, layer 2, and layer 3, and think about it's a perfect graph. You know, layer 1 means maybe you have like 10 different nodes, and layer 2 maybe another 10 node, layer 3 may have another 10 node, and from each node here you think about that they are kind of like connected. And you know, I'm not going to go detail into this, but one of the important concept is that suppose you take this one hidden layer neural net, and then you add something that is called nonlinear activation. So neural network, when you think about like one node, like you know, and you have an input coming to that node, and that then there is an output from that node. When you are taking the output, you add any nonlinear function. So if you just take a one node, you think about like that's just like the way you compute any function, and then if a number is coming, and then the same number you just take the output, right? Then there is no change in that number. Now you can multiply with something, maybe like you have x coming to a node, and then you multiply x with w, then you have wx, that is the output. So that's an output where it's just linearly changing it. And that actually doesn't work for many of the modeling purposes. So what you want to do is you want to add some nonlinearity. And you use any nonlinear function there, and then take the output from there. So this is an important concept in computer science and mathematics, that if you take like one hidden neural network with nonlinear activation, that can approximate, you know, think about like any function, you know, ignore that continuous function on a compact domain. This is a very specific way of defining functions on the finite bound. But think about like one hidden layer neural net that can actually approximate any kind of function. And that's a very powerful mathematical statement coming from long back, the history of computer science and neural net. Now, so another important part is when in that theorem, like the neural networks can approximate any kind of functions. In that theorem, there is nothing mentioned about how many nodes you need. So in the neural network, you need a bunch of nodes, and then you think about like this approximation will require, actually it can require an infinite number of nodes. So you think about like a layer, you think about like one layer, and you have like a whole bunch of nodes, and if you increase that number of nodes to infinite, then I think it is possible to represent much more complex functions. Now, in this large language model, this kind of models, they have depth. They are using not one hidden layer, they are using many layers, and there's a reason for that. So again, like not going deep there, but think about like that depth actually makes the approximation of function efficient. So if you are coming from other disciplines, you can think about like whatever mathematical equation is important in your discipline, and if you want to represent that equation, then you can have a deep neural net which has like whole bunch of layers, and that can actually be able to represent that particular equation. Now, and in this world, like how to pick the function, there's something called RNNs, recurrent neural networks, and then there are types of RNNs called LSTMs, GRMs. These are early sequence models, and the one of the reason, and they were initially used, but they were very hard to parallelize. These are like large models, a lot of parameters. Computation is very hard. So computation is one of the challenges. So what becomes very important is transformers. This is basically the beginning of this LLM revolution. So transformer is actually very important. So there's a paper by Goswami and his co-authors from Google DeepMind. They had this paper. You probably have heard about this paper if you have read about this area. It's called Attention is All You Need. And they are when I'm talking about this transformer architecture, there are so this picture is actually explaining that, and if you look carefully in this picture, there are like two sides, and one side I have written is BART. It's a very special type of large language model. It's called an encoder model. That means it is something that is useful to represent any kind of words in a language. And then on the right side, it's written as GPT. It's a decoder part, which means the encoder is basically the model that will help you to create a representation. And then once you have a representation, you want to decode that, and you want to find out of what it is. And that part is known as the GPT, which is basically the variants of how ChatGPT is made. That is this part. And now, if we the important part here is if you look at like how the input is coming here. So both of these they look very similar. So input is coming here, and then the input is a vector. So if you have a word, you convert that word into a vector. That vector is the representation of the word. Imagine somehow you converted the word to a vector, and then you have a sequence of word. All the sequence of word is as an input, and then ignore the positional encoding right now. That will go through something called multi-head attention. I'll explain that in a minute. And then this add and norm, these are all, imagine like if you know programming, if you have seen any programming language, how this is written, imagine all of these boxes, right? Add and norm, feed forward, then add a norm. These are all some kind of construct within the neural network literature. So some kind of constructs in the neural net, and a very specific construct. And when I'm saying construct, that just means some very specific way of computation. So I'm going to go to the next slide, and I think this is a much easier expression to understand. So, and this is the equation for the attention. So if we have a sequence, if you have a sequence of words, typically the way we want to compute how important, like how way we want to convert these words to some kind of vector. So we pick for each token, we pick like three vectors, and we call them like query, key, and value. The basic idea here is if you have a sequence, you take one token and then try to identify how this one token is actually related to all other tokens in the sequence, and that's how you and these three vectors are actually there. You assume basically you create these three vectors for all tokens, and think about like the first one for which you want to construct all of these three vectors. You multiply that the query vector with key vectors of all other tokens. You take the dot product and then use something called softmax. So this is nothing but, suppose you have this, again, the example I was trying to explain with is a cat is sitting on a mat. And then if you think about a cat, I have an example. Let me just go and directly go to the example. Okay. So think about this example. So you take this word cat, right? And then you are trying to compute like how cat is related to all other words. And imagine someone has given you some vector for cat and some other vector for sat, on, the, and then what you do is I'm going to take this cat vector and then take a dot product with the vector at sat. And that is going to give me some idea about how closely related they are. And I do that same for all the words. And the expression here is kind of like capturing how each word is connected to all other words. We take the softmax. Softmax is nothing but it's a mathematical trick to convert all of these numbers to something that will map them between 0 to 1. So you can consider them as probabilities. So you kind of like, after you have this operation done, what you have is for each of these words, you have some vector that is representing how they are, how cat is related to sat. If sat is the closest word, then maybe and most related word, it should come right after cat, then it will have a higher number. And then we kind of use another vector, we call it value vector, that's kind of give it some kind of ranking here. So these three vectors, again, like there is a there's a deeper understanding here. You can construct these equations in many different ways, but this is like one of the ways this attention equation construct. So you can just imagine mathematically that you use this equation, and then magically you get the output of this entire operation. Think about this as a matrix operation because you are operating with lots of vectors and batches of sentences. At the end of this operation, you get all these three vectors for each of the token, and this kind of represent how this token is important. These three vectors for each token, when you combine all of them, they will help you to model how this token is important with respect to all other tokens. So it's kind of like starting to do your likelihood model. And then I talked about few other terminologies like residual connection, layer norm, and these are all kind of, so if you are from electrical engineering, I think you can think about like how the distribution of electricity happens, and you can just intuitively think about, okay, I'm going to, for using this equation of attention, I magically construct for each word some kind of vectors. Those vectors represent these words in a way that captures how this word is related to all other words. semantical, right? It's a semantic space. And if you are on the electrical engineering, you know that suppose you have these networks, right? Because when neural network you're thinking about, it is a it is a bunch. It's kind of a graph. You can think about your load distribution graph in your electricity, right? When you are designing like how electricity will be transferred from one place to another place. So these are different ways to make sure that, okay, I am computing a lot of these vectors, I have a lot of depth, I don't want to lose signals here, I don't want to lose the numbers here. So you have like different kind of modulation. And this residual connection is nothing but you are just like using some kind of signal processing trick to make sure that you are able to propagate the information there. So the intuition important here is you are kind of like computing for each token. If I give you a sentence for each token, in that sentence you are trying to come up with some kind of vector. That vector will represent how this token is related to all other tokens, and then what you want to do is you want to process this vector every layer, and you want to attempt to do the very similar kind of operation. And you want to make sure that the information computed in the first layer, they are not getting lost. And this layer norm is another technique that normalizes each token's vector. If you are from other engineering discipline, you know that normalization is very important for a lot of like numerical operations. It's for numerical stability. And then we talked about the attention. Think about like just that is a one small function. Now, when you are applying this attention, you are kind of like coming up with these vectors for each token. Now, in order to make sure that you are able to come up with the right kind of vector, they use something called multi-head attention. It's nothing but instead of one attention vector, you are sort of like trying to hedge your bet. You are trying to make sure that, okay, I am not going to only construct 3 vectors. I'm going to construct many vectors. I'm going to have like many attention and many set of 3 vectors, and hope that combination of all of this will give me a better representation. Again, that is something very well known in statistics, that it's just simply you are averaging many things, and you expect that average will be more close to if you just randomly pick one. That's the basic idea. Then there is something called position encoding, which is also important for this, in the attention expression, what we have talked about. This is taking a lot of the dot product, and it's kind of like exhaustive dot product. So you have A, B, C, you are taking A, and then you are computing all of these things with A and B, A and C, and then C and B, all in every way possible, like every pair. Now, that thing is position independent. So that means there is no concept of order here. So how do you bring the concept of order? That brings this position encoding thing. So that's a trick to add order to add the order information there. Now, we talked about this encoder and decoders. So BART is an example of encoder, and GPT-2 is an example of decoder. So BART came in 2018 from Google, and this is a very specific type of attention because it's a representation. So I think if we go back to the example, our example is here. Yeah, so go back to this example. In BART, the way it is modeled is, suppose this is the sentence, then I put a mask here, and that is the sentence, that is the word I'm trying to predict. And then I try to compute the distances of this part with all other tokens. Okay. So that's called bidirectional. just know that the GPT-2, this is where we are trying to do next token prediction. So that's why this is the decoder part, and all of the LLMs which came into existence from ChatGPT and all of these things, they are like GPT-2 variants. So I'll not talk more about that. I'm going to go to more useful things. So in GPT-2, each prediction, it uses like all previous tokens in a fixed window that we explained before, and GPT-2 overall the window size is was really 1024 tokens, and that just means that any word you want to predict, it will be able to look at all other 1000, all other tokens before it. Now this is called context window. Like what is the input size, of any such models, and it's fixed at training. So the modern LLMs, which we are seeing today, which we are using when we are using GPT, that has scaled up this context window. Imagine that whatever is your context window, that many words will be there, and then you will be having a lot more of this attention equation you need to apply for all of these words. That just means that you are doing a lot of computation. If you have a large context window, that just means you are doing a lot more computation. And that's where it has scaled up. So typically, if the transformer block, I apologize that I didn't really prepare this for explaining from neural net, which is like very basic. But if you study the neural net and the transformer block, the picture we have shown, I think the important part for you is if you think about like what LLM is, then the easiest thing to think about is this is actually it. That you can, the first layer of this neural net is kind of like the token and position embedding, the concatenation of that. And then you have like bunch of transformer block, exactly the block I have shown you. Think about this block will be, you can actually have one mathematical equation for one block. Once you know that equation, you know what transformer is, right? So even if you do not have the computer science background or ML machine learning background, imagine that you at home, you just look at like what a transformer block is, then you know even today the GPT that you are using in ChatGPT website or Gemini website, all of them kind of like variants of this. There are like bunch of transformer block. There are several transformer block, and left side it's talking BART, and again like BART is not used as much now. So right side is what you are seeing. And all of these language models, they are outputting probability distribution over a vocabulary of words. That's basically it. You have a bunch of transformer blocks, and again, like there are like lots of innovation happen on making this thing efficient. I'm going to talk a little bit about how these things are trained. Now, in order to in machine learning, in order to create these kind of models, and these models, you have like many weights, many variables, right? Variables. And if you want to figure out like what weight you should be, what is the value of this weight should be, you need to train this model. When I'm saying training this model, you will be using some data, and then you will be feeding that data to the model and trying to see that whether the prediction is correct or wrong. If the prediction is, whatever prediction is from a scratch model with randomly initialized, you take the output, you compute some kind of loss, and then you try to optimize this model. Again, optimization is exactly similar in mathematics, like how you optimize things. You basically try to minimize a loss, and minimizing means you will, if your function is y equal to fx, you will take dy dx, and then you want to make that expression to 0, and then you compute like how compute the gradient there, and this is called gradient descent. So you known as back propagation in neural network. It's nothing but you just differentiate entire thing, and you are trying to adjust the parameters according. It's if you have studied numerical methods, this is basically it. You just like take the equation and try to optimize the equation. And the numerical methods, if you have studied, then there's a lot of like stability issues, and a lot of the stability issues are here, and a lot of these things, since this is like computing many different things, and it's a chain differentiation, so there's a lot of like numerical issues to make sure that things are stable and working well. So the important part here is the GPT-2, which came around in 2019, and that was a much more smaller size model, like around like less than 2 billion parameters, and that was trained with web text corpus, like 40 GB, around 40 GB, the 8 million documents. And one of the important things is they cleverly, the OpenAI team, they cleverly picked clean documents. So if you want to train a model for languages, you need to train with nice data. If you train it with bad data, that means the language is really poorly taken example, then I think then you will not be able to train it. Okay, so and there are like a lot of like tokenization aspects. I'm going to sort of like omit those things because I think these are a little like need a little more background here, also not like super important. So one thing is that in GPT-2, it is around like 1.5 billion parameter. And then if you hear about GPT-3, which came later, it has 175 billion parameter. So one of the interesting thing is from GPT-2 to GPT-3, the OpenAI team, they found that, okay, so I have this 2 billion parameter mathematical equation. If I'm increasing the number of parameters there, and then what happened, then I see that my loss in language model is reducing. That's an interesting discovery. And with that discovery, they put a lot of money, bring a lot of compute, and purchase a lot of GPUs, and then try to create a much larger model. That is GPT-3, which is, you can imagine, 175 billion parameters. They were trained with 300 billion tokens. That means the kind of like words they have trained with from the language, it has seen 300 billion tokens. Now in Google, at the same time, they actually found that no, if you train it in this way with 175 billion parameter and 300 billion token, there's a problem. What they found in Google researcher, that if you choose a number of parameters, there's a relationship with how many tokens it should be trained with. And they figured out that, okay, 175 billion parameter model, 300 billion tokens, that's actually little less data. So the model really is trained with much less number of tokens. So they claimed that, okay, if you have you can actually have a much less number of parameters that will take less money to train, and then you can increase your data size, and then you will get a better model. And that's what they have shown. So it's called Chinchilla paper. That's an important paper here. Now I'm going to avoid some of the slides because of the complexity involved there. So okay, so this is important for everyone for engineering discipline, that all of these transformer equations, whatever I'm saying, under the hood, everything is matrix multiplication. Anything you are doing there, entire thing, you can just make bunch of matrix multiplication. Matrix multiplication is actually one of the most expensive operations in computer science. Now, for that, you know, if you just do a matrix multiplication, it's like it can be cubic if you do not follow any special operations. So it's just impossible if you have too many matrix multiplication, large matrix multiplication. So parallelization is very important. GPUs actually come there. Again, that's a completely different concept. So I'm not going details there, but just think about that. There's a whole bunch of matrix multiplication. Without parallelization, you cannot simply train the model. By training the model, when I'm saying training the model, you have a lot of this matrix multiplication. So people, so OpenAI, Google, they started understanding that we need more data to train this model, then the models will be better. So they started figuring out like how to get more data. And in GPT-3, one of the observation is that suddenly GPT-3 models, when they have this 175 billion model, they observe that you can actually prompt that model, and they can actually solve a lot of problem only with prompt. It doesn't need to be trained with that example. So, and that was a big discovery. And there's a lot of like research papers on how new abilities are found. So think about like you have a small equation versus when you are using these billions of parameters. It's kind of trying to represent our brain, and suddenly interesting properties emerges. Suddenly the capability non-linearly increase. So this is a very interesting phenomenon. And that just means that you give it a new problem and it has not solved that problem before. Like humans, it starting to solve that problem. Okay. So there are a whole bunch of evaluation benchmark data set that are used to look at like how good these language models are. There are like names thrown here. I'll share the slide so you will know that. You don't need to really understand these things right now. Okay. So we talked about that. Okay, we take like whole bunch of data set and sort of like take this equation. We train this model by fitting this data and then differentiating this equation, trying to minimize the loss and optimize and come up with these parameters, and then trying to come up with the optimized mathematical equation. Like optimized math, you can think about like if you know like linear equation, like W1, X1, W2, X2, it's basically very similar. Like all these W1, W2 values, you will come up after the optimization. Okay, so what has been found that okay, so after the language model is first time trained with all of these things, it is kind of ready for when you feed some words, it will try to emit the next one. But then in real life, the problems we want to solve, that we want to ask a question to ChatGPT, we want to get a right answer, not really the next one. So we sort of need to figure out like, okay, I have this model, how do we really nudge the distribution to nudge the distribution so that we can actually solve like interesting problem, like question answering, summarization, all of these things. So the way this happened is then they figured out that, okay, let's just divide the training process in two steps. Like one is the pre-training class, when we are training the core language model. Another part is post-training. After we have this language model ready, we are going to train it further for special kind of data, like what kind of problems we will see. And again, like I'm not going to go deep into this, like after, like, unless someone asks me question. But I think the important part here is there's a pre-training part, there is a post-training part. In the post-training part, we have many different mechanisms that can be used to adapt the language model for real life tasks like question answering, summarization. You can have like a lot of these different tasks. Now, this is and again, like you can consider that the terminology picked for all of these post training purposes, you can call them like fine tuning, basically fine tuning the model for specific tasks. And then there are like many different ways of fine tuning. Again, like not going details here. Now, so we talked about this GPT-3 and the Google paper. Google found that, okay, GPT-3, they have not used right kind of data set. We need to use more data if we are using that many parameters. And then with that knowledge, GPT 3.5 came. Now people need to figure out like data, right? How they will find the data. They already used web scale data already. So, and then people realize that, if you have clean, good data, then you get a better model. They started using the code data because a lot of programs are there in the internet. They initially didn't use the programming data, but they started using programming data. And then they came up with the GPT 3.5. So interesting thing is that with the code data, the moment they added the code data, suddenly the performance improved. So as I mentioned before in the beginning of the lecture, that there's this concept of perplexity. If you think about the code is a very structured data, very non-ambiguous. The programming languages are much less ambiguous compared to natural language. And that's how, if you have a structured code, meaningful code, and if you're training the model with that, it will actually learn that very quickly. So two things observed, that if you add the code data anyway, it is actually improving even the natural language ability. And then it is also able to generate pretty good code. And that was a big discovery. And that was the ChatGPT moment. This built on this GPT 3.5 and then something called Instruct GPT for alignment. When I'm saying alignment, you don't want GPT to give you really bad answers. So alignment is making sure that it will give you an answer that actually humans will like. And then it's fine-tuned for, if you have multi-turn conversation like what you can have with ChatGPT. There are these other concepts. These are actually good to know, that whatever ChatGPT is doing is when you are inputting with some kind of question to ChatGPT, some kind of conversation chain, and then basically you ask, like, tell me the future of Earth, right? What is going to happen in next decade? ChatGPT will give you some answer, good or bad. These days it's giving good answers. Now that thing, the whatever number of words you will enter there, that will go inside and it will be input to the model. The model is actually outputting only one word still, which is the next word, because it's just trained to output that. And then that next word is feed again to the model, and then it is outputting the next word. So there is a separate program. So when you are getting the output in ChatGPT, you are seeing an entire paragraph coming out, an entire paragraph coming out of ChatGPT. But that is coming out because there is another program that's actually querying this model again and again, and then making this paragraph. And how that program works, that's actually important. And this temperature, top K, top P, these are all these things. Top K is, I'm going to explain one. The others are also very similar. So top K, for example, a language model output a distribution, probabilities of next word. Top K means you are picking top K probabilities from there and just picking one from there randomly. So it just changes it from being very deterministic to a little more, creative, or, because not necessarily the best probability. If you just take always the first one, then it is 100% deterministic. It's going to, if you input same set of word, it is going to respond with one particular word most of the time. There's still randomness because there's like randomization everywhere. Now, so that's the chat GPT moment that we have seen in 2022. So this is kind of the overall like how the LLM has come to chat GPT kind of product. I'm going to skip some of these things. Okay, so now that you have the chat GPT kind of product, imagine 2022, what people started thinking that, okay, I have to train these models with so much data, and still it is actually not doing that well for a lot of benchmark tests where humans can do very well. It's like nowhere close to human. Right? So people are trying to think about like what is going on. So then people kind of like started thinking that, okay, humans are really much more efficient because humans, they don't really remember things. They're not like parrot, right? Humans, they reason about things, and they can actually conceptually understand a lot of things. That's the way humans actually come up with good answers for a lot of things. So that's how the concept of reasoning came, that the people thought that, okay, there must be, and then the other thing, the other observation is that they figured out that, okay, if you have this GPT pre-trained, the language model, if you ask it to do something step by step, or if you give it like a whole bunch of steps for a problem, it actually performs better. This is called chain of thought reasoning. And all of these indicated that maybe something is there. So so what happens there? Yeah. So the idea came out that, okay, so this is basically the steps. If you want to explain the steps, you have, it will generate a lot more tokens. And if I suppose allow the model to come up with the steps fast, then the model may perform actually better. And that is the core idea for the reasoning model. So you, instead of giving just input and output, you train the model with whole bunch of steps. So model can take the input and get model can take the input and then get to these intermediate steps and then get to the output. Amazingly, this actually started performing much better. Now there are many different ways of training model in this way, but I think you should know at least like one way, which is you take the same architecture, you have an input, you have an output, and you take a lot of these intermediate steps, and then you add that to the output. So you think about input is coming with, output is coming with the intermediate step. You train the model, same model with that kind of data, it converts, it becomes a reasoning model. And then there are like different other ways of making it better reasoning model. One of the ways, as we discussed, like sampling for top K, for example, we talked about that. You can actually make that process very sophisticated. If you have a lot of like intermediate tokens, which is intermediate steps, you can generate multiple steps, and then you can pick the one which may be close to your correct result, which is more likely to give the correct result. So the process of sampling there, that program becomes more complex. And that also means that it's going to take more compute, more time. And that's why you see these models like O1, O3, which are reasoning model, that actually take more time to come up with the answer. But one thing to know here, this token sampling-based reasoning, it's not what is in computer science considered as planning that requires backtracking a lot of like very specific phenomenon. but this is still like very significant. There are like whole bunch of reasoning benchmark. I think one of the thing may be interesting to you, this ARC benchmark, where humans actually perform close to, I have this data, humans perform close to 100%, and where this GPT-4 used to perform at 4%. And then this reasoning model, they started performing 75 to 85%. DeepSeek R1 is another reasoning model, came from China. So I'm going to go here. Let's go. So there's like the other understanding came, if you observe like GPT-4 and all of this GPT-4o and all of these models, they started becoming multimodal. So what people found that, okay, with the text data, we already exhausted a lot of text data. Now, what about if I also give it image data? Can it reason about image? So that started this multimodal part. There is very similar kind of approaches, but think about it, you need to represent the image as a vector, give it an input, and sort of like correlate images and text inside the model. I'm going to talk about more yeah, maybe like this is another. So the one of the thing is, if you have a very large model with, if you think about like GPT-4 or more recent model, they can have 1 trillion parameter. Just running, and when you are querying a GPT or a model like that, you have a huge number of matrix multiplication going on. In order to conduct that, you need the hardware. So it is not only the training is expensive, the inference can also be very expensive. So how do you make it cheap? That's actually one of the important area in computer science. These are the names of the techniques. I'm not going to go in detail, but maybe like I'll talk one line. So this MOE, KV caching, speculative decoding, these are different techniques, like how do you make like inference faster. So KV cache is nothing like we talked about this attention equation, which has K, V, and Q matrices, and this KV cache is so that we don't need to compute this again and again. We kind of like try to cache some of these K and V weights for all of the layers in neural net. Basically, caching some of these things so that next time we compute this, it will be easier to we can just have a lookup instead of doing the actual multiplication. Speculative decoding is the name is fancy, but it's basically you just have a smaller model. When you get an input, and when you get a query, you first run a smaller model that generates some tokens, and then maybe like small number of tokens you generate with a large model, but you start a small model is helping the large model to get things done much more cheaper. And then the MOE part is basically it's a change in the architecture in a way that you don't need to compute every matrix multiplication. You kind of like per token it will use a specific set of path, and then you in inference time when a particular task comes, then it will maybe like not utilize the entire network. You will use a subset of the network. It's basically designed to optimize the inference. So this thing that the reasoning and the and the initial like LLM building of LLM, one thing was missing, that like if you want to actually do some real task, you need to have something with memory. So that's where agents come. So LLMs are stateless, and they don't backtrack. I mean, basically you cannot have LLM going back and iterating with things. So how do you like design programs that will do your book your flight ticket or conduct some of the tasks you want to do, like what you are seeing in the research agent, for example, in ChatGPT. For that, you need the agents where it will have an LLM, it will have a memory. LLM is kind of like acting as a brain, and then you have a memory, and then you are computing something, storing something, going to the next step. You can kind of like design like a program. So agents are very powerful. So um, uh, so what I believe that, with LLM tools plus verifier, like, when you have memory, LLMs running, a lot of LLMs are able to identify what tools to run, and then it can, you can execute a search for identifying things and then feeding it to LLM. You add all of these things, you can get a superhuman level performance on many of the digital workflow. So yeah, so this is basically a very historical shift in how computing is done and what kind of capabilities we are seeing emerging from the AI. Yeah, so I think I will stop here. I think we spend some time on understanding this thing. I want to hear like questions from you guys. Actually, we'll have like the rest of the time.
Any question from participants? Any question from anybody?
So, any question about GPT? Maybe may not be related to this presentation. Any question about Chat GPT? Why it does what it does? Anyone?
Okay, nobody is asking questions. So
Okay.
may I ask some? Okay, one
Yeah,
question.
yeah.
Uh, what challenges might arises when uh, integrating an external controller with current LLMs?
Okay, that's actually a very good question. So that's in the agentic world, you want to control tools with LLMs. LLMs will trigger that this tool should be used, and then suppose you are actually controlling that tool in an iterative process with LLM. So you need to make it in a secured environment. It's very similar when you are trying to execute a lot of programs with LLM. So you need to sandbox it and like separate it out, make sure that it's a safe environment. It will not go into a direction that is unintended. For computer program, it can do always a lot of harms. Like if there is a bug there, if there is a virus implanted there, or it can even go to a wrong direction. In future, LLMs will be able to. LLMs are already able to generate programs, so it can generate a particular program, then it can run it. So, but you don't know what program it is going to generate. So if you are running with this kind of external controller, you just need to make sure that every time it is running a step, it's going in the right direction. So the safety, security, that is very important, that you need to make sure. That's a very good question. What is the difference between Gemini and ChatGPT? There is not, conceptually you can think about, there is no difference. They are very similar kind of mathematical model. Like Gemini use a different tokenizer than ChatGPT. There is a slight architectural difference the way they have done it. They have different size, but essentially they are very similar. The entire ChatGPT, you can think about one mathematical equation. Nothing else is there. One equation. There are a whole bunch of matrix multiplication happening there. That's it. Same for Gemini, same from ChatGPT, but they are trained differently, trained with different data. Size is different. There may be slight variations in what exact function they are using internally, because all of this, the entire neural network, you can very simply think about, you have just a complicated mathematical expressions which are f of all this. You just give a long list of like function inside function, and then expand it. That will give you uh, a complex function. So that's kind of neural net. So that's conceptually very similar.
Okay, I have a question. We heard that DeepSeek is using much less computational power than ChatGPT. So, what is the basic difference between the architecture of ChatGPT and DeepSeek?
So DeepSeek used actually many different optimizations, and the reason they were able to train the model with much less much less cost. The primary reason is they started from a trained model. So they took the Llama model, they ran the Llama model that was open source from Facebook. They generated a lot of data from there, and that data, when you're generating data from model, that is slightly higher quality because you have like less noise there. So that is one reason. They started using something called MOE, that mixture of expert that I just briefly mentioned, that actually make the inference cheaper. So there are like bunch of optimization they have done that also make both like inference cheaper and the training cheaper. But primarily it is like much more cleaner data. They are already using a pre-trained model, and then they have used reasoning to improve the model.
Okay. And what I have noticed when I have used ChatGPT for the first time, ChatGPT was trained with data before 2020. Now, that was different version of ChatGPT, and now when I am using ChatGPT right now, even I ask question on recent topic, ChatGPT is basically asking or searching web to give answer. So it is basically not solely based on training data. It is using recent data.
Correct.
So how this happens?
Okay, that's again another very good question. So this is an example of agentic AI. So what is happening when you are giving it a query? ChatGPT is trying to identify whether there's a recent information required for this query. If the recent information is required, what it is trying to do is it is conducting a web search. It's downloading the data, and after downloading the data, it is vectorizing all the data, and then identifying some component that may have the answer to your question, and then feeding that entire thing to the model, and then the model is answering the question. So it is called like retrieval augmented generation, this kind of processes. So it's using that, and then it's doing tool calling. So it has become like quite sophisticated in that way. And today it can search the web. Tomorrow it will be able to search a lot of other things, like other archival or other things, or like do a very precise kind of computation. So it's just more like example of agents coming into the picture.
Okay, thank you. So another question from audience: what is the difference in using ChatGPT and Perplexity AI?
Oh, Perplexity AI is a company which started using as a wrapper of these models. So these model companies, OpenAI, Google, or Anthropic, they are training this large model. They are coming up with the models, and they are like, as I explained, the mathematical equation for each of these are not like too different. One is better than other. Sometimes another one is beating another one in different benchmarks, based on like how they are trained, right? They're not going to be significantly better or worse. That is possible, but that less likely unless there is a breakthrough in that something come in the mathematical equation. Perplexity started as a wrapper, so they kind of give you, you pay some money and then they will decide like which model to query instead of subscribing. And all of these Anthropic, Gemini, and ChatGPT, if you want to use them in the professional mode, you need to pay all of these sites. Instead, you can pay Perplexity, and they will decide where to send your query to get the best response, because there are like too many models now. And now the DeepSeek is even cheaper. So, and then Perplexity started also developing their own cheaper model, which is feasible. Just like the way DeepSeek has developed the model, much cheaper. You can take a much larger model, and then you can sort of like generate data and then create a smaller model from there. And that smaller model may not be as good as the large model, but you can, today, you have tools to make this reasonably good. So yeah, so Perplexity is yet another company that is providing the interface to the user, and they're trying to make sure the output is better. They have done some innovation in terms of making sure the answers are correct. They're doing some verification after getting back the answer. So they are like adding a lot of other things. This is an example of a Silicon Valley company. They started at the right time with an interesting idea, and that clicked, and they have become big. There's another question.
Thank you. So next question is, sir, can you get the PPT?
Oh, the PPT, the PowerPoints, the slide PDF file. Yeah, I'll share that slide.
Yeah. Okay, fine. So next question is, can you suggest best website to download recent data set?
What kind of data set? For training this kind of models?
Probably.
Sir, image data set for medical diseases. Like cancer, brain tumor, MRI data set and all.
Top of my mind, I cannot tell you like where you should be looking at, but I think if you actually, this is a good query for ChatGPT deep research or Gemini deep research. They will give you details. They will search all the web and answer your question much better than even you can search in Google and find the answer. I think there are like quite a bit of image data for cancer and diseases, open source.
Okay, thanks.
Okay,
Hi,
next
hi,
question is,
Hi.
in Meta AI and ChatGPT, which one is more efficient?
I do not have an answer. I think there are like benchmark tests for, so efficiency means which one is actually good, which one is fast. I don't have the specific answer. This is there are like different benchmark tests. I think Meta has done quite a bit of work in inference part, how to make the model very efficient, because they have this entire Facebook data. They have a lot of recommender system. Meta in general, they have done very good work in how to make the computer systems very fast, and they have also done very good work on the inference side. They have a lot of open source also. But yeah, ChatGPT has been doing pretty well too. I mean, they recruited a lot of very good people in this area. And it's Silicon Valley is a small area. Same people, they work in different places. But and in terms of number of techniques used for making the inference fast, they are very similar. So again, like just like the model quality, the inference quality will be very similar. The best in the inference, best in class has been Grok, the Elon Musk company. They actually specifically invested on a lot of like low level things to make the inference faster. But yeah, there's like a lot of details there, and how Grok make the inference faster.
Okay, next question is, which support vector machine model is used in ChatGPT?
So support vector machine models are not used in ChatGPT. These are all like neural net. But you can think about like when you are computing this attention mechanism, the computation itself is very much can be, if you study theory, it can be actually mapped to kind of like kernel machines there are like papers on these areas. So there's a lot of similarities there, but it's not technically support vector machine. Support vector machines are more, there's separate optimization models. There's a geometric understanding, like how support vector machines are optimized, much more simpler. You cannot scale it up to billions and trillions of parameters. So that's the difference. It's a neural net, and support vector machine is a different machine, different model.
Okay, so Priya raised his hand. You can ask your question, Priya. Priya raised her hand. Please
Yeah,
ask
hi.
question.
Yeah.
Okay.
So is there any difference between ChatGPT on-prem ChatGPT as well as cloud?
Difference between ChatGPT and Claude?
No, on-premise ChatGPT and cloud ChatGPT. So if a company don't want to share this data, it's not interested to share the data outside. So if they got ChatGPT into the on-premise into their company, so will that make any difference?
Between Claude model, no, in terms of model, there is not any technical difference. So
Okay.
now ChatGPT is not, I don't know whether they are allowing you to use in on-prem, but that need to be something that OpenAI needs to do that. But there are models, open source model, that you can deploy on-prem or on your laptop or desktop, like smaller model, and that will do some work there. And all of these models, more or less, they have like very similar architectures. In terms of equation is very similar. It's just like different ways of training, different kind of size. So they are like little bit like slightly different. You can train a model really poorly by training it with bad data. So the data quality is one important area. Google has been doing search for a long time, so that's how means I was expecting that they will come up with very good model, and Gemini 2.5 is actually excellent model. And of course, like ChatGPT, they have been doing very good job. Anthropic is also doing very good job. And they all have a little bit different ways of training. Anthropic has something they call constitutional learning. You will see in Anthropic website, they have a very razor sharp focus on safety of neural network. They look at layer wise. So there are like a lot of interesting papers came out from Anthropic. So their models are doing, I would say, very well, and competing well with ChatGPT and Gemini.
Okay, thank you.
Okay, next question is, can you suggest a place or a course where we can learn this language modeling?
I think one of the best place to look for is Stanford University. They run several courses on language models. Like they have courses on NLP in deep learning, computer vision and deep learning, basic deep learning course, basic machine learning course if you want to start from ML basics, and then they have these days courses on the LLMs from scratch, and the material that I tried to cover here, which I realized a lot more, but they actually cover a lot of these things in detail if you take a semester long course. And they also are, it's very nice that they kept all of this older version of the course online for free. So that's a very good place to look at. And the other source of learning is ChatGPT or Gemini itself or Claude. They can teach you very well if you ask it questions. And now there is ChatGPT Learning came out. That's just a prompt inside. You can use that model to interact with it and learn. So there are like multiple ways of learning. And in YouTube, there are also good lectures from other faculty. One of the best course I found from CMU, Professor Viksha Raj. I really like the way he teaches with very first principle approach. If you want to really clarify your concepts, that is, his courses I will strongly recommend. Viksha Raj from CMU, he has taken courses on deep learning, so he'll cover like computer vision, NLP, a lot of these things. Yeah, and then if you want to start from basics, then start from basics of ML. The Stanford courses are also very high quality.
Okay, so next question is, are there any specific frameworks or best practices for coding the core systems of an LLM to increase the computational efficiency or reduce the GPU load?
So you want to understand, are there any framework for improving the efficiency for the inference, right? Yes.
Yes.
Okay. Yeah. Yes. Yeah. So there are like a lot of framework. There's a lot of details there. Inference is actually very important because you need to have like a lot more inference running than the training, because a lot of people will be using these things. So it has been studied a lot within this small amount of time, because it's a lot of money also in that area. So the frameworks are, you look at like low level hardware. There are like things they call it like hardware accelerator, different kind of GPUs, TPUs, how you will optimize your program for running in GPU, TPUs. Then there are like techniques like this MOE, mixture of experts, where instead of running the entire network, all computation, it will choose a particular path and then make your computation much less for a particular query. Or like speculative decoding, which is another one where you have a small model helping the large model. So all of these techniques like KV cache. So there are like a lot of these techniques coming out. So these all and in terms of framework, all of these things are available as like a lot of these things you can actually code up right now if you want to write your own program in Python using some of the libraries available from Hugging Face, or there are some other libraries. Facebook is making available, or Grok has made available. So there are like a lot of frameworks and code libraries available for these things these days. And again, like hardware part is CUDA. This is the library coming from NVIDIA, and one can actually, a lot of the Grok, for example, they are very well known for inference right now. They have done a lot of optimization there, blazing fast. They did a lot of work in the CUDA level, the low level. Basically, you want to finally optimize everything, you need to optimize for the hardware. And that is basically NVIDIA's framework. And they have like a lot of training for that.
Okay, so the time is already over. So thank you, Anjan, for your lecture and for these questions, means for these answers, smart answers, good answers. So this is a very high-end topic or cutting-edge topic. So mostly what we discuss in our lecture, those topics are at least invented, say, 20 years ago. But whatever you have discussed today, those are invented, say, maximum 10 years ago. Okay, so that is not easy to discuss. So that may be the starting point where people will understand LLM, and then means will get some idea about LLM, and then if they are interested, they can means train themselves by other courses, by doing other courses. So thank you, Anjan, for
Thank
your
you.
lecture. And I think this is not the night time of giving lecture at California. It's you started at morning 5:30, so
Yeah.
it's a really a tedious job to give lecture at morning 5:30. Okay, so again, thank you to you.
It's my pleasure. And yeah, I could have probably simplified the entire thing quite a bit. I realized that I made it more like computer science oriented. But yeah, that kind of like, I think if you go through the slide and look into the specific topics and look into the lectures, I think it will be helpful, because it is actually covering, if you are able to understand all the topics discussed here, you probably will be able to develop LLMs, like, not like DeepSeek, but maybe like something like GPT-2.
Yes. Okay.
Okay. Thank you.
Thank you.
Mhm.
So uh, we can move to the next session because next speaker is ready. Means he has already joined. So uh, it is my pleasure to introduce Dr. Sumit Misra, Chief Innovation Officer at RS Software. Dr. Misra uh, has had an illustration career spanning more than 3 decades in the IT outsourcing industry, where he has contributed in various capacities as an engineer, project lead, project manager on large and complex projects. He, his extensive experience now enables him to guide leading companies in the payment industry in formulating technical strategies, staying ahead of emerging trends, and building customer centric competencies. 1 minute. Okay. Uh, at RS Software, Dr. Misra plays a pivotal role in strengthening the company leadership in payment domain by managing the RS School Payments and RS Payments Lab, while also institutionalizing best practices in knowledge management. He holds a doctorate degree in engineering from Jadavpur University with his research focused on STEAM data analysis. Today, we are privileged to have him with us to share his insights. Please join me in welcoming Dr. Sumit Misra. Over to you, sir.
Thank you, Dipanjan. So I'll be sharing my screen and the presentation, and we'll take it from there. Just a moment. So I think you can see my screen, or is there
Yes,
any? Okay,
Yes, sir.
yes,
okay, thank you. So I'll be talking about protecting digital payments, leveraging advances in AI. So if we look at today's world, we are seeing lot of things are happening. That means we are getting many new modes of payment like real-time payments like UPI, then CBDC, that is central bank digital currency, stable coins, all of these are coming up. And there are multiple payment rails and modes are there. So what it is doing is it is increasing the surface for the fraud. With AI powered impersonation, it's becoming very difficult to understand whether an AI is talking or a person is talking. With all of these, the money that is moving in the wrong channels that are getting laundered. So June 2025 report says that in worldwide about 2 trillion US dollars of money is getting laundered. And in order to cover the the KYC and the money laundering and all of that, there's a there's a compliance that is demanded from the by the various reserve banks and the compliance bodies, and that is increasing the cost. So for example, in EMEA, the bank compliance cost in 2023 was $85 billion. So either you lose money which gets laundered, which is in the tune of $2 trillion, or to protect it, you have to use somewhere between $100 billion in order to protect it. So these are not small amount of money; they are very large amount of money. Right. So with this as the background, we are trying to address or understand how we can use AI to protect the digital payment world in digital payment ecosystem in the world. If you have any questions, please feel to stop me and we can have discussions. Because this is I don't have very large number of slides, but what I want to share with you is that in this journey, fortunately, we in RS software have the privilege of protecting your data, digital payments data, to a large extent. So RS Software is a company which built UPI, and it is also the company which is protecting multiple, is has provided the NPCI's fraud and risk management platform, which is protecting UPI and many other channels like IMPS, like AEPS, the RuPay cards, and all of these gets protected using our system. So I'll share some of the real life data and real life experiences. So if you have any questions, please feel free to interrupt and ask questions. So I see Priya has hands up. So if you have any question right away, I can answer. That's not a problem.
No, no, I think it's from the hand is raised for previous speaker.
Okay, 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 okay. Okay,
It's
that's
not
fine.
for you.
Okay, that's fine.
Okay.
Okay, so let me continue. So how does the fraud manifest itself? How we get to see the fraud? One is that when at the very initial stage, when a person is trying to register either in the bank or in the app or in anywhere in the getting registered within the payment ecosystem, at that time fraud happens. That means your identity is somebody's identity is stolen, so somebody is getting in as not that person but somebody else. So that part is called identity theft. That means it's not a the person who is claiming to be. Now that is something happens before the entire transaction happens. Then during the transaction, there are two ways the things surface as fraud. One is consumer is completely unaware that your account has been taken over by somebody as is trying to move money to some account, or and that part is called account takeover. So the consumer is not even aware that your user ID password or PIN or SIM swap or stolen card, whatever things have happened, and that person doesn't know when the fraud is being perpetrated. They don't know it. Third is the person is very well knows that a transaction is happening, but the problem is instead of paying somebody you are thinking you are paying to a wrong person. I'll give an example. After the COVID, so there was a campaign that was started by Prime Minister's office. It was called PM Care Fund for the COVID affected people. And then there was a handle given that okay, you can do an UPI into that particular fund, and that your money will be taken from there. So within a very short span of time, that handle was manipulated and like PM Scare or PM Cares. So the name was changed slightly, and immediately 15-20 accounts were created from different banks. And people started advertising and people started paying. So in our country, billions of people are there. So in with that huge population, billion plus population, even if a fraction of person pays 100 rupees, so crores of rupees get accumulated within 15-20 minutes, and then they run away with that money. So that part is that the consumer knows that I'm paying, but he doesn't know that he's paying to the wrong person. That is called authorized push pay. And the fourth in the entire manifestation phase is called money laundering. Now, yes, the money has now moved into an account of a illicit person, whatever. Then the money needs cannot sit there because they need to be immediately taken out. Like crores of money taken in the PN Scare fund, they were like in a rush to take that out of the system into various other accounts, and then through that multiple ways it gets taken out so that you cannot trace or catch that entity. So there are basically four. One is before, the two we see is the during, and the third one is after. So this is the cycle of the fraud manifestation, and what we will discuss is how we protect in each of these phases. So any questions? Okay, no questions. So let me take it forward. So now with this, we have to have various fraud protection strategies for all of these four areas. So now identity theft. We all know that KYC is a very standard way of, you know, registering a person, and from time to time bank asks that you refresh your KYC, you give your credentials and all of that. KYB is know your business. This is a business account, not the KY. KYC is consumer or customer and B is business. So there are mechanisms of doing that business updates there. Third is that you, whenever you are registering somebody, you are trying to get the credit score, the CIBIL score, or other type of scores are there. And then there are mechanisms to check whether identification is generated synthetically. That means it is, there is nobody like that. All the data that you are getting is fudged. It is not a real person. And then there is something called Sanchar Sati in India, which is providing a mechanism so that you can get a list of telecom companies are sharing lists of SIMs which are blocked or which are stolen and all of that. And so when you are registering a particular identity, a person in the system, you can check against that whether he's using a wrong SIM which has been registered as fraudulent. So now this is easier said than done, because when you are trying to compare, KYC is like name and then your address, then your Aadhaar, PAN, and all of these are there. All of these are, so there can be same name, multiple people. Address, there are many areas. You cannot only think about metro cities, it can be rural and other cities where your cooperative banks are working. So their addresses are very, addresses overlap. It can give the, it can say that it is in, say, Aurobindo Park, and there is no house number there. So thousands of people can be in that Aurobindo Park. You cannot segregate. Now, Aadhaar is a very good mechanism of identifying, and your PAN number is. So matching matching of those Aadhaar to the name, if it is done manually, not using techniques that we currently do, that your Aadhaar linked mobile phone gets a OTP and that is getting registered there. So those are digital ways of registration. But there are many people who doesn't have a mobile phone. So how do you do their KYC, KYB stuff of things in online? So you have to match them. Matching documents, which are in India, it is a very, very large number. That is not easy. So without your IDF mechanisms, TDF, IDF mechanisms, you cannot actually match within any particular time. So there are lot of AI algorithms at play when you are trying to match information for looking at the identities. So that's one part where you're using the AI. I will go to the account takeover and authorization push payment. Now, this is something that happens during the payment. That means at most you get 200 milliseconds in order to look at a transaction, decide whether this looks like a sheer fraud and you decline it, or it looks like a sheer good, you don't stop it, or it is in the gray area, which you can say that, okay, I'll hold for some time, I'll get some manual review before I approve that transaction. Now, to do that, one needs to look at multiple things. They need to look at the behavioral traces, how the person usually behaves, whether a purchase, a relatively elder person will not purchase at 11:30 in the night from an Amazon. So these are behavioral factors that gets used. So you have to do a lot of behavioral profile collection and storage in a way that you can match. Second is the device fingerprint. The device fingerprint is whenever the device that you use for making the payment, that device on the device, for example, you have Amazon or you have Phone Pay or you are using Google Pay, whatever, they actually have a mechanism to look at the device and collect lot of information about the device. What is the screen size, what version of Android you are running, or whatever phone you're using, what is the angle at which you hold the phone, what is your typing speed. All of these are put together and assigned to a number which is called the device fingerprint. Because if your device gets stolen and you don't have a really good protection uh, in the password or in the pattern, then it can be easily opened and then people will start purchasing things from there, making changes. So, and many of the all of our phones nowadays have the bank information, either Yono or whatever, HDFC, and then they can get into there and hack into your system and start moving on. So the device fingerprint is important because it is endpoint uh, connectivity. So whenever you're using UPI, if you're registering your for the first time, you'll notice that it sends a SMS to the phone and it automatically reads the SMS and does something. So that is called device binding. Device binding includes something called device fingerprint. So our algorithms which we have for the in the UPI, that has something which is uh, which is used for this purpose. The third mechanism is activity sequencing. That is some sequence of activity, say activity 1, 2, 3, 4, 5. This looks like a pattern, which is the fraudulent pattern. Now the problem is some of the fraudster may skip certain steps and still this pattern will be a fraudulent pattern. So it's not a one-to-one match of the pattern. First of all, you have to understand that what is that activity that the person is doing. Second is there a sequence of events? Third is, if it is a sequence, if there is any dropped sequence, which is uh, without which also they can do a particular fraudulent act. So if we look at all of these, then there's an activity sequence. Now you have to understand we are transacting in, say, in UPI at a phenomenal volume. It is unthinkable volume that we are handling. So right now, when there's a peak during, say, Diwali in the evenings, like similar time, 7:30 to 8 p.m. and during the Diwali, just before Diwali or the Durga Puja and all, we reach in the range of 20,000 transactions per second. And there you have to look at those activity sequence of each of the person, understand that the sequence is matching or there's a skip. So without using AI, you cannot do that data churning in order to come to this conclusion. Another factor is the payment context tracking. That means if you are using your, say, RuPay card and you're trying to take out money from an ATM which is very close to a railway station, that's absolutely fine. But doing that at 2:30 a.m. in the night is a context that doesn't look right. Not that it will stop it, but it can, if you're taking 1,000 rupees, it will not stop. It will sense that it may not be the correct, but it will not stop it. But if you take 1,000, then you take 5,000, then you again take 15,000, then that is a sequence which is not right. It will stop at that point in time. So the context, activity, all this behavior, everything comes together in order to give you a context, and that becomes important to do this. And for doing all of these, we use rules as well as AI models, because we have to respond within 200 milliseconds. Because when you are purchasing from UPI, you hardly do that within 2, 3, 4, 5 seconds. You start getting responses, even 5, 10, not more than 10 seconds. And the 10 seconds has a large latency of the communication between the mobile and to the server to your bank, and from bank to your mobile, and all. There are lots of legs of transaction that happens. So for fraud management, you are left with around 200 to 300 milliseconds to do all of these jing bang in order to protect yourself. So all of these require uh, some mechanisms of using advanced mechanism in order to protect. So any questions? So I don't think there are any questions. And if there is any question, please feel to speak up. No, not a problem. Okay, so this is the strategy that is taken. Now we'll see how this each of these gets implemented. So now let us see the first part, which is the KYC and KYB. It is very interesting that if you are doing a KYC in a traditional manual form, it took 1 to 3 days for the document collection, human review, and all of that. AI powered KYC is taking 2 to 5 minutes. Verification accuracy has gone up from 85 to 90 to 95 to 99% using AI. Fraud detection is limited because it relies on the human to check the documents and do apply everything. AI powered systems can do that, the same fraud detection 30 to 50% more using it can detect deep fake, duplicate ID, behavioral biometrics. So you have to blink your eyes and all of those things are there. So yeah, so using all of that it does. And we see that the cost for doing a KYC was earlier $5 to $10. So roughly $10 is nowadays about 800 900 rupees. Say somewhere 400 to 900 rupees is the cost that was coming for manual things. Now it is has dropped to 0.5 to $2, so which is significantly low. And you cannot scale KYC because it was human intensive systems. You cannot just say okay, now you do it at that speed. It cannot be done. But in AI powered eKYC, millions of verification are possible. So that is what we done. In the business area, the KYB area, manual systems took weeks, which can be done in hours now. In business, there's a very complicated concept of ultimate business beneficial owner. That means who is the ultimate person who gets that, you know, uh, revenue or who gets that money. And it is difficult to find out because there are multiple layers. Now, using Graph AI and the ownership flow, which are mentioned in the during company registrations or merchant registrations, one can look at multiple graphs at one time and figure out who is the end beneficiary. Is it somebody who is a criminal or whatever? That can be figured out easily. Then comes the money laundering and sanction screening. So there are thousands of names that are there. And if you are just trying to match the names, uh, that is not right. And that fails multiple times because the spellings are different, abbreviations are there, middle names are skipped, and it becomes difficult to do manually. Using fuzzy match, this can be done much better, right? Then you have the compliance staff involvement. That means people who, how many staffs are there in order to, this is a compliance staff, because if you are registering somebody who is in a business to just do frauds or just move money, then that is a compliance issue. So you have to have 5 to 10 analysts per case. That means per business who is getting registered to do that. And in case of AI, it is just one analyst reviewing AI flat risks only. So it doesn't need to look at everything. It needs to look at very handful which are marked, right? So now this is the KYC KYB area. So it is 10 times faster using AI, cheaper, and ratio detection ratio greater than 95%. So obviously you will do that. Now, if I look at the models that they use, there is large amount of information that is provided. And nowadays, many of this information can be extracted online using API also. So all this information, and then the list of blocked SIM from telecom, and special software which can detect synthetic ID detectors. If all of these things are put in a box, which is AI ML driven, it can generate a KYC KYB score very fast in minutes. And this helps to make the process of KYC KYB so much faster. Okay. Okay. So let me move on. Okay. So this session is planned between for 90 minutes. That is from 7:30 to 9. And in this time frame, India UPI, we will see about 1 billion transaction happening. In this billion transaction, the worth of this value will be in the range of 1.25 lakh crore rupees. Out of these, 60 million attempts will be there for the fraud, worth 7,500 crores. And all of these are our systems will prevent. And still there will be some which will go in our outside of our blinkers. There will be about, in this 90 minutes, 260 cases worth 4 lakhs that will not be able to detect. And this system is powered by our product, which is called RS IntelliEdge, which is running in the NPCI. NPCI is the technical arm of Reserve Bank of India, and that is protecting that 60 million attempted fraud, 7,500 crores is saved for the consumers. So this is the implementation completely built in India, and it is running and protecting all the people in India. So now when we talk about those 4 ways of protecting, this is a result that we see, and this data is almost correct because exact data cannot be shared. This is a approximate data, but this is very close to what you can understand. It looks scary because if the 60 million attempts were not, we could not catch them. So in this 90 minutes, about 7,000 plus crores of rupees would have been gone off from the consumers to the criminals. Okay, so how do we do the real-time fraud detection? So it is worth noting that there are multiple techniques that are used. One is a very standard method which is called hotlist. That means you have a list which has identifiers for the good and the bad. So one is called the whitelist, and the other is called the blacklist. So the whitelist has all the good names. That means even if somebody is transacting with that phone number and system is trying to say it's fraud, it is not fraud. It is good. And there is a huge long list of the bad guys. Now you will know that if, and you have to remember that 200 millisecond is all you have in order to protect using all these techniques, right? So if there is a millions of data that are there, say a few million is for the card numbers, few million is for your virtual payment address, a few million of the account numbers, few million names. Now, whenever a transaction is coming, you have to check across those 5, 6 types of millions of names instantly. Yes, there are techniques that are provided by AI and other software which can do that fast. But before that, you have to do indexing, you have to do all sorts of things in order to get ready for doing that. Now, it is not ending there. A new blacklist item can come, and you have to update the list. Now, as you can understand, with 15,000 transactions per second happening, you cannot even wait for a second to update this list. So you have to have a design so that you can update the list on the fly, and your transactions are happening at 15,000 transactions per second. So that is, so AI and uh, performance designs that go in. It's a very simple. If it is only 200 names are there, searching is like very simple. But if there are 20 million names or 20 million items in the list, it is not the same, because you have to do it within 200 milliseconds, and you have to update the things as the hot list information comes in. So that is the hot list complexity that we are talking. Second is behavior. The behavior is a little more complex. As the transactions happen, you have to capture the behavior. That means, okay, this person does transaction, say 5 times a day, or he does in this 5 times a day, he doesn't do any transaction in say up to 7 p.m. and between 7 p.m. and 9 p.m. he does all the transaction, or he does that 7 p.m. to 9 p.m. transaction mostly in the gas station for filling his scooter or something, and then does some grocery and some mobile top up, this type of things. So think about the complexity of maintaining and updating per person information in the profiled memory. Now here the memory distribution has to be complex, the update has to be complex, and there are very large number of things that needs to be uh, considered in order to update these profiles. And these profiles, if you aggregate these profiles, you get a picture of how somebody is spending in a, say, city like Calcutta or North Calcutta or say South Calcutta. You can actually see how people are purchasing things. So there is, if you see the UPI usage in general, you will see a peak happening between 6 a.m. and 7:30 a.m. Then it falls, and then again it picks up mostly during the lunchtime. Again it falls, and then after the office hours, which is 6:37 to about 9:30. So that there's a pattern to it. So it was very strange to see why 6 a.m. to 7 a.m. there's a peak, because that behavior was not being able to, we could not understand, is it a right behavior, wrong behavior, what is happening. So it's figured out that nowadays when people go to buy milk in the early morning, they also pay using UPI. So that is called a milk, we have named it as a milk spike. So whatever I am saying is profiles that needs to be stored at individual level and compared with the current behavior in order to get a match. Now, this is a typical problem between a sequence, an update, and a match. And obviously, you cannot do that at that volume, at that, I would say, frequency within that very small time of say 10 milliseconds, because you can for 200 milliseconds you have to do all of these, right? So you cannot give it everything to the behavior, and behavior is one of the most complex things that is there. It gets updated every time somebody is purchasing something, so that update is also a complex thing, right? Next, we see identity. That means your mobile number is an identity, your account number is an identity, your device is an identity, your IP address or your uh, Wi-Fi router. All of these are some type of identity. So all of these identities have a play, and that is used. For example, in say Google Maps, they say that you keep the Wi-Fi on so that you can get a better location service, because it is not your Wi-Fi. It is all the Wi-Fi's in the town, they are mapped. So whenever you are moving with your Wi-Fi on, your phone senses that there's a Wi-Fi. You cannot log into it, but the Wi-Fi ID or the IP address of the Wi-Fi can help the app to decide, okay, you are in this location. So that's a very smart way of doing it. So that is a locational factor that gets into this. And then your activity is there, which is sequence of transaction. So in this entire thing, I missed one thing, is the geolocation. So geolocation is part of the behavior because your phone has a geolocation tracking, and that is used, the lat long is used in order to see whether where you are using. And if you're buying something here, within 5 minutes you cannot go 220 kilometers and start buying from the other point. So all of these gets part of the behavior. Now with all this information, you can build rules and you can build models. So all these transactions that come in, so this actually so this actually shows the transaction. So when a transaction comes, it is evaluated against the rules, and the transaction is also sent into the AI and machine learning models, and that also gives a score. So when the rules and this score come together, you get a holistic score, and that holistic score either tells you it is good or it is bad or it is doubtful. You don't know whether it's good or bad. So this is in general the the mechanism that is used in order to do that, do this segregation or finding out whether a transaction is good, bad, or maybe. Any questions?
Actually, sir, that the behavior is one of the things is required to be incorporated in the so
Your voice is breaking. Can you please repeat? Or yeah.
sir, actually the behavior you have said that this is used for the model to detect fraud, right? So the fraud always track the user what his transaction and what time. At that time, the fraud is doing that fraud. At that also be uh,
I cannot hear you. I think you're in a.
sir, can we hear me, sir? Hello.
Yes, I can hear you, but you're breaking in between. Yes, you said that during the behavior, if you're making a transaction, whether it's fraud, yeah, I could hear up to that.
Yes, sir.
Yeah. So what it is typically done is that if a person is does a usual transaction of say 600 rupees at the groceries, and suddenly he is doing a 15,000 transaction at the groceries that night, it is marked as suspicious, or it can be marked as fraud if that grocery is very way distant from his home, and it can be declined. Did I answer your question? I am not sure.
Oh, no. So actually, the timing of the transactions. Hello.
Yes, yes.
Timing of the transaction always that helps the uh, MI model to detect the fraud.
No, no. So the AI ML model, you're saying whether the AI ML model detects the time sequence part? That's what you're saying?
Yes, sir. Yes, sir. Huh.
So no, it is not the LSTM type of models that are used there. So what happens is, if you have, because you have to understand these are individual person's behavior. It is not collective behavior. For the collective behavior, there is a mechanism that we are using in the AI ML model. That's the first filter. But when you come to the individual person model, you cannot use AIM, this LSTM type of things, because it's very, in a month, that person does only 100 transactions or 200 transactions. That is not enough data to do a profile and do an LSTM for them. So it is best for rules to do that. So that is the reason we use mixture of rules and models. Did I answer your question?
Sure, sir. Sure, sir. Okay.
Okay, okay. Any other questions? Okay, so let me move. Okay, so this is what is happening in the on the fly, and this is happening at a very high speed in order to do the protection. Now let us try to discuss a little more of each of these boxes and see what is it that's happening. Okay. So what is done is that for the good and the bad, you subscribe to paid lists. So there are multiple paid lists which are there, which are provided by multiple companies, and you have to purchase those lists upfront. And whenever that list comes, there are different periodicity, maybe once a day, twice a day, or it can even be once a month, twice a month, or something like that. So different feeds are coming with different formats, different periodicity, and you have to homogenize that information and put into this hot list. So that is for, and all these sources are not very clean data, but you have to apply certain data enrichment techniques, and that technique has, in some of these techniques we use AIML in order to make them, because that information is important, so we use that in order to do it. So as we run the system, we are generating alerts and declines and all of that. So and even good part of it, which is good list, good information. That's a non-decline. That means pass through. So alert, decline, pass is happening every single second. Thousands of this is happening. So as from that list itself, we get information, and first of all, you have to get that information in a particular way. So you have to do clustering and all of that. Do that, and those again become a feedback into the hot list. So it is not only that you are getting information from the subscribe list, but you can also get information from the things that you are processing, because it can be that somebody was using a particular SIM card, which the phone got lost, or the SIM card deactivated or something has happened, and then the transaction is not going through, and then that is a decline that is happening. So you will want to update your hot list with the decline information. You have already seen that in your system. So you will not wait for the police to or the telco company to list that as something that it is in the gray list and you have to stop it. You can get that from the API calling into that particular telco feed, but that will come say 7 days, 10 days later. Your system probably has seen that much earlier, so you can use that in order to update the hot lists. But there needs to be clustering, segregation, and all of these techniques. Some categorization. So all of these are done using AI ML type of stuff. Then I was mentioning how to update the list without service disruption. And this is very difficult thing to be done. It's not easy because there are millions and millions of lists are there. All have been indexed. So you want to insert something into an index list without stopping that, without actually blocking the read of that particular index list, right? So this is a different technique. It's not an AML based technique, but there is there are techniques that are used in order to do that. And then once you update one list, you have to be cognizant that it is not one system that runs. There are 3 to 4 data centers in India which is handling all of these. So you have to percolate the copy across the multi-regional deployment wherever it is there. So not only you have to update at one place, which is difficult, you have to pass that copy to all the data centers that is handling all of these. So that is the second part of it. And this update is complex. So we do that using certain techniques. Now it is the behavior part. The behavior part, the information, if you see, it is very simple to understand. It is a frequency, that means count, and is the amount, which is the aggregate of a time telescoped unit. That means maybe from midnight to 1 hour, 1 a.m., 1 a.m. to 2 a.m. Or there are various granularity of time frames that are used. And for each of the time frames, for each of the MCCs, location and payment method, you keep the frequency and the amount. That is what you have to do. But doing that at an individual level is complex. Here the problem is not that you will update a particular list, because updating is easy because a person will at least take 1 to 2 minutes to do another transaction, and that is good enough to update the list. So we can do a read lock and do the update. But the problem is you have to distribute it across the various data centers. Second is that whenever the individual all the individual don't have their thread, they are also bucketed. So the buckets means the way you will handle the buckets, how will you distribute how you do the strategy for the bucketing depends on how the data, the pattern of the data that is there. So in order to do that complexity, we have to do certain amount of a different type of clustering here and different type of bucketization. So this is a very simple part. Then you have something called merchant risk score. That means all of these we are talking of frequency, amount, etc. from the perspective of a consumer. But whenever you are paying some, say, merchant, the merchant needs to be scored as well. Whether the merchant is a fraudulent merchant or is not a good merchant. So what happens is merchants get, unlike the frequency and the amount which is infrequently updated for consumer, for merchant it is frequently updated. Because if you look at a particular, say, pantaloons or a shop that has multiple tills, everybody is paying and there could be same QR codes there. So the volume depends on the type of the merchant and what is happening there. So there the thing that we talked about, the frequency and the amount, which is easier for a consumer perspective, it is not easy for a merchant perspective. So they have a different factor. So that has to be considered. Then you have the velocity checks. That means what is the frequency of the swipe, that or usage or the payment. And all of these have to update the profiles both for the consumer and for the merchant at at certain periodicity, and the update should be non-destructive. If you put all of this together, it is a NP conflict problem to be solved. You cannot do it. So you have to do some uh, assumption and optimization at every stage to get the best of the whatever best you can do, because you cannot do everything. It's not possible because it will defeat the cap theorem, the consistency, accuracy, and the performance. All the three cannot be met at the same time. So without violating the cap theorem, without violating the things that you cannot do, you have to still do this in a particular manner. So this has lot of techniques which are derived from the AI and other perspective. Right? Okay. So let me now talk about the any questions on this. I can just wait if you have any questions. Okay, I think there are no questions. So let me progress to the next stream, which is identity. Now, identity has a different set of problems. Identity is like your account number, device ID, mobile number, IP. Unfortunately, they are not one, means relationship could be one to many, so the profile is to this. But if you look at a device, if you look at a IP, so for one IP, there are multiple phones. One account number may be shared by, it can be a joint account. If you go to the villages, or if you're going to the tier 2 cities, or if there is an means aged person, then the device is shared as well. Mobile numbers, in many places, mobile numbers are also shared. So it is a many to many linkage that is there. So the identity is not easily determined by these things, which sitting at a metro or a city, you will not be able to understand. But what we are seeing is this is also not a unique method of understanding that particular person. So whenever we are saying that this particular device has made so many transactions, this is the profile of the device. The problem is if somebody takes the device and that person goes shopping, that is very common in case of tier 2 cities. Right? They share everything, password, everything is shared, and every people do that. So you cannot stop that. So that gets into a multiple behavior profile against each of those IDs. That is another problem that you have had. Next is somebody has opened a new account, bought a new mobile, bought a new device, got a new phone number because the earlier one was deactivated. How do you map that information? Because all the information that you have kept against the mobile number is now lost because that person's mobile number is deactivated. Not only that, after 3 months, that the mobile number is getting used by somebody else. So there is a aging of information that has to be done. So you cannot maintain and keep the profiles for ages. It will not work. Right? And then you have the activity. Activity is fraudulent activity, have patterns that we have said. Like identity theft situation, people, they typically check a balance, make a small transfer to see that the thing is working. and then they make a large transfer just before midnight and just after midnight, because every day has a 20,000 limit or 50,000 limit, whatever, there is a limit to it. That is given by the bank. So that limit, they use that limit on the both sides of the midnight, and they do this thing. But this is a very used pattern. So if somebody is doing it, we can actually see and stop the fine, stop it at one point. And these sequences may not be same. I'm just giving a simple equation flow, but there can be other flows and other cases, other use cases where the flows are not same, but still it is a fraudulent pattern. First of all, detecting that this is a fraudulent pattern by human, we can understand looking at this, but there are many flows which are, it is impossible for human to figure out. So looking at sequences to figure out possible, fraudulent activity pattern is also done by using AI. So that is also something that we do. Right. So we have covered all the four things, whatever we had discussed in this flow: hot list, behavior, identity, and activity. So we went a little down, deep down on each of these so that you can appreciate where the things happen and how the things change. So now we will talk about now that this part, if you look at the so now the identity part we have discussed, this part we have discussed how we are going to stop it, and now that they have, suppose somebody has been able to do all of this and finally move the money to particular account. The money is now collected in some account and it is ready to be used by the fraudster. It is that position that we are talking right now. So if it is that situation, it is called, this phase is called the money laundering phase. So there are four activities. You accumulate the money from illegal activities that we have understood. This has placed the money into a financial system. So the money has already come into the financial system. Then there's something called layering. That means this money is transferring the money to hide the origin of the funds. So there will be multiple movement of money. It will go from an account of SBI to an account of HDFC, then to an Axis Bank, then to some Bandhan Bank or rural bank where it's difficult to trace. So they will do all these hops and joins in order to move there. And then finally returning the money for the money launderer to spend. So this is the collection, spending. Any questions? Is there any question? Okay. So this flow is the money laundering flow: placement, layering, and integration. Now, if we look at this one, this is across banks, across accounts, across everything. So how do you handle this? If I look at the 2023 FICCI and CII report, 5% of the India's GDP has been under the money laundering illicit trade, which is in the tune of 159 billion US dollars. So it's not a small amount. Every bank needs to report something like this suspicious activity report, suspicious transaction report. Every bank do that, but they do that once 15 days, once a month. By that time, in case of real-time payment, money has come in, money has gone out, and they have been put into wrong use already by that month. So you have to have a mechanism to catch that much earlier. Now let us look at what is it that we are trying to do. Okay, so there is something called a mule account detection. Very recently, India has launched a particular solution which is sitting at the central level, which is RBI level, where it can do all of these. What it does is it creates multiple types of node. Bank account is a node, individual is a node, IP address is a node, phone number is a node. So they are all these nodes. And between these nodes, whenever there's a money flow, that is called the edges where you have the money flow. So you create a graph of the entire flow and multiple types of node, multiple types of edges. So transacting account to account is one edge where your money is flowing between account to account. So account to IP address, account to phone number, all these are part of that entire network that is created. Then you start using, now this is a very, very wide, large graph, right? So then you have to use graph neural nets in order to detect circular payments. That means it is going in a loop. That means funds are moving between groups of accounts. And this is being done to obscure the origin, right? Unusual transaction flows. That means a dormant account suddenly becomes receives large sum of money. This happened mainly for the the Jan Yojana accounts that are there. Suddenly, people saw a lot of money coming in, a lot of money going out, and all of that. Then a cluster of accounts, that is a group of accounts that are not directly linked but are all connected to a common suspicious node. Each of these are looks like very clean, but in some path they are connected to a suspicious or confirmed bad actor, right? Then there's a problem of centrality. That means the graph neural net can uses to measure the closeness, centrality, and between the centrality to identify the accounts that act as the central hub of the bridges. So basically, proximity detection between the bad account and other accounts. What is the distance between them, right? So graph neural nets do a really good job at this and to flag this transaction very fast. They do not need to wait for months and weeks and to do that. They can do it in hours. So this is mule account detection is something that government of India has already rolled out, and you can see the name if you want. And they use all these techniques to do that. So this is AI, but in the graph neural nets, in the graph area, right? Now, in order to do anti-money laundering checks, there is lot of manual factors. Now, all that will detect, but you cannot actually go and catch some first. That it cannot do because it has to do all the checks. So if you look at the entire flow of the KYC and the money laundering part, there are many boxes all marked in red. You can see these are marked in red, which are very manual intensive. And this becomes the target for use of AI. Not that all of these are converted, but this is something that has been means highlighted, and now this is Gartner. McKinsey has created this report very recently, June 2025, which are saying that guardrails for growth, building a resilient payment system. So they are trying to say that these are the areas where you need to apply AI in order to protect it's like the guardrail for the payment systems. So this becomes another area of discussion, research, and all of that thinking in order to how to do all these things. So this is banks will love to have it as a solution, right? Now I come to my penultimate slide. It is showing how the frauds, the digital payment increase, and the fraud is increasing, and how we are protecting. So out of all the transactions that happen in UPI, and even UPI being the largest, which is more than 84% of the entire digital payments in India. So if you just look at the UPI itself, 25% of the transactions are non-payment transactions. They are like balance inquiry. You look at confirmation of pay. All of these are there, and then 75% is the payment transaction, right? So you have to bridge all of these in order to have that in order to reach that do a fraud. So if you look at 2023, so there were 2 million cases that were reported as fraud, and the 2,500 crore was the fraud that has happened. 2024, 2.8 million cases were reported and it was 4,400 crore of fraud. 2025, the estimate is 2.9 million cases will be reported and about 55,094 crore will be the fraud. So the rate at which, and if you look at the rate at which the transaction are increasing in UPI, they are phenomenal. That is increasing at the rate of 17 to 20% year on year. But you can see the fraud cases and the fraudulent amount are not increasing at that rate. So it is kept in check. Now, if you look at the card payments or the internet banking payments, so FY24 saw 29,000 cases of internet banking and card frauds amounting to 1457 crores. That means each case was 5 lakh rupees of loss. 25, the numbers have come down, but then the loss is 4 lakhs per case. UPI, which accounts for the 84% of the entire digital payments in India and 55% of the digital payment fraud. So 50% less than 50% of those fraud are less than 10,000 rupees per case. And if you look at 24 and 25, in 25 till date, there's 6.32 lakh cases reported and 485 crores that has been the fraud. So roughly 7.5, basically 7,500 rupees per case. So this is where the protection is working. This is data that is showing. In August 2025, there were 20 billion UPI transactions, and the amount was in the range of 25 lakh crores. So out of that, we stopped 6% of the by count all the transaction. We did not allow it, and 3% were alerted, and 91% passed. So if you look at this, you can figure out that this and this amount, the protection that we are seeing every day, every minute, or every second in India, and this is getting powered by a system that was built in India by us. There is no, it is made in India. It's nothing to do with some other country's solution. So I think that brings me to the end of my lecture. So I'm now ready and open for any discussion.
So thank you, sir, for your excellent talk. What you are doing at RS Software and what you are doing for India is really excellent. So I'm just asking the audience if they have any question they can ask. Any question from anybody? Okay, nobody is asking questions. So may I ask one question?
Sure.
When you are using graph neural network for calculating the distance between two accounts, what is the distance matrix that you are using?
So we use multiple, graph elements, and that multiple graph elements, and then we basically transpose and provide that on normalize it, and then we use that distance algorithm. So it's not very straightforward because it cannot be used in a straightforward way.
Okay. So, okay. So, Pidas, if you have any question, because you can write your question, because when you are
Yes.
muting yourself,
Yeah,
then there are a lot of noises.
Yes.
So, Pidas, you can write your question in the chat box. Any question from anybody?
Hi. So, is there any chance of recovering the once the fraud is happened? So, can we get, I mean, recover it from after a fraud?
That depends on the channel. Yes, you can do that. You can register a case, and that's a different flow because it's so once a UPI you have made a transfer or RTGS UPI, if you have made a transfer already, so these are called non mutable transactions. So if once that is happened, it's happened. So you have to do everything to stop it before the money movement happens. But once the money movement happens, you can still that's a banking channel. You can say that's a fraud that has happened, and you can even register for uh, the crime digital crime branch. All of that is there, and there will be investigation, and many people get back money. That is there, but that has already happened. So that's beyond technology. That's then regulatory aspect.
Okay, thank you.
And you have that you are using rules as well as you are using AI/ML model. So
Right, right.
my question is how you are getting those rules? It's a done manually or it's derived by AI?
Yes. Yes. So I have not kept the rules in details here because it's the focus was on AI. What we do, we have a federated rule engine. Now, what is federated rule engine? Is that NPCI can provide rules. So there are about 200 odd rules the NPCI can do. But then every bank can have their own rule. So by that, basically, I'm doing a crowdsourcing of the rules. Using that crowdsource rule, which is in the range of 20,000, so 200 is NPCI. But if you look at all the banks and they give all their rules, so when you crowdsource that, then you have very, very large number of rules there. And that is created by the risk analyst of each of the banks. And then there's a processing that happens to deduplicate the rules, put them in the central or in the banks. All of rule management happens, and then we use that for the detection. It is manually created, and this is where Dr. Datta, your algorithm can probably be used uh, to look at all the labeled fraud and creating rules by itself, automatically. Probably we can try there once we get some access to those data.
Yes, yes. Okay, any question from anybody? Please feel free to ask question. We have another 5 to 6 minutes. He is the person who is using AI in the financial sector, means for last 2 to 3 decades. So yes, yes. Any question from anybody? Ask question.
I think we are standing between the dinner and the participants, so it may be there may be you know
Uh,
are the various gateways use the same fraud detection? CS. So this particular solution is sitting at the center. That means at NPCI. So any transaction that you do in India on the NPCI channels pass through this particular system, and there can be multiple gateways that is there. The PPT, I have already shared the PPT, so you can collect it from Dr. Dutt.
Uh, okay, I will share it. I will share it. No problem.
Okay. I'll share the latest version. Maybe I've made some small changes, so I'll
Yeah,
share
yeah.
with you.
Okay. And one more question that suppose you are using some rules for detecting fraud. Okay. Now these fraudsters are also changing their working methodology. Means
Yes.
then the rules
How
that
do
may
we?
be good, say 5 years ago, that may not be good
Absolutely.
for today.
Yes.
So
So what we
what
do
type of
is
work you
rule.
are doing?
Yes, yes. We do something called a rule profiling. That means you suppose there are 15,000 rules. So we look at how effective are the rules, means how many frauds it is catching in a time sequence manner. So if the rate falls, then that rule, so there are two ways of looking at it. That means the rule is very good, so it is not letting some fraud, type of fraud to be happening. And the other is the people have moved away from that particular mechanism. Now, interestingly, if you look at the rate of the fall, from that it is possible to detect whether it is something which is effective and you have to keep it, even if there is no detection happening right now. People are not going that way. But, or it is something that is becoming stale. That means you can now switch it off and uh, use some other rule. Because every rule takes time and we have to process all the rules simultaneously, because the system cannot be that if there are 10,000 rules, it is taking 50 milliseconds, and if it is 15,000 rule, it is taking 75 milliseconds. That is not permissible. Everything has to be done in 50 milliseconds. So all rule have to be executed in parallel. So, but if we can reduce the number of rules and rationalize with time, which we do regularly, uh, it is very that is needed, because otherwise the system will block itself.
Okay. Somebody is asking question regarding Jamtara gang.
Jamtara. Yeah. So in Jamtara, if I remember, it was authorized push payment. That means you are sending money but to a wrong person, because they were intercepting in between and sending it to somebody else. So yeah, those things. So now you don't hear Jamtara because we have plugged all the holes there, and those this type of I would say rules and models that are there, they're still there. If you remove them, somebody will know and immediately start misusing them.
Okay, so one thing is that suppose we have a set of rules and after some time we are changing the set of rules. So are you also changing the sequence of the rules? In which sequence the rule will be fired?
We initially had that sequence thing, um, but the problem is sequence does not matter, because you have to check all the scenarios. So it is, earlier we could not do it parallelly. Now we can do in parallel. So that is the reason we are, sequence is not important.
Okay. So you are checking one transaction with respect to every rule,
Every, yeah,
right? Oh, all rule that
all
that
rules,
must pass through all rules.
all rules.
Okay, okay.
There
Any
is one more
question?
question, I think.
Yeah.
Can evolutionary game theory be used to get the best food strategy?
I didn't get your question.
It is written
Can
in the chat box.
evolutionary game
Okay, okay.
theory be used to get the best food strategy?
Can we use game theory to get the best rules? That's what you're saying, right?
Yes.
Yeah. So it is so dynamic. It may be possible to do that, but how do you simulate a situation where your profiles are changing and your uh, the data quality, data characteristics is changing, and then you are looking at the rules how it is effective. So you are changing uh, so many parameters out there that creating rules or selecting rules using the game theory. So there's a where you can say prioritize that these are the 80% and this is the next 20% type of things. That it is not practically it is not very applicable. The information is there. Somebody can do a research and find out whether that works or not. But what we have seen is that that is not the best path.
Okay, so last time I'm asking that is there any question from anybody? Okay, so probably we don't have any more questions. So I will share slides. Don't worry about that. Dr. Sumit Misra has already shared his slides, so I will share that slide.
I will share the updated one with you right after this call, and then you can share that.
Okay, okay, I will do that.
That is
So
version 4. Yeah, version 4.
yeah, yeah. Now you have already shared version 4 with me.
No, no,
So
there's small updates. I'll share this one.
okay, okay, no problem. So after you will share with me, then I will share it in the WhatsApp group that I have created for with all participants. Okay, so thank you again, once again, for your wonderful talk. And we got some insight that how at present our system is working in the banking sector and what RS software is doing in the banking sector. So thanking once again for giving your time. Uh,
Thank you.
so
Wonderful.
So okay,
Okay.
so this
Okay then.
so with this I am okay. So with this I am announcing the conclusion of today's session. So tomorrow we will join again at 6. Okay. So
Okay.
can I
Thank
close it?
you.
Thank you. Good night, everybody.
Thank you very much, sir.
Okay then. Thanks.